Another example, here we have 1-butanol in the presence of sulfuric acid. You can have 1-butene as your E2 product. And then since we are in the acidic medium, so this can get protonated again and form a secondary carbocation. In the presence of hydrogen, a proton will add onto this carbon, CH3, and this would be carrying a positive charge, secondary carbocation. Now, once a secondary carbocation takes place, a hydrogen from this carbon can be lost to form the 2-butene. So it would be something like this, CH3, CH, CH3, so this is the intermediate. So a water molecule can take this hydrogen and form the alkene and form 2-butene. So if you start with 1-butanol, even though you would expect to have 1-butene, you would get 2-butene as the major product due to this process. Dehydration is stereoselective. What does that mean? Now we have a secondary alcohol here in the presence of sulfuric acid. OH get protonated, forms a good leaving group as a water molecule, and then you have your carbocation formed. Now this carbocation, once it formed, it can form an alkene, more substituted alkene, or it's 2-butene. You see it's going to be 2-butene in both cases. But now there are two possibilities. It could be trans 2-butene or cis 2-butene. And then the formation of trans 2-butene would be the major product compared to the cis 2-butene. Because the stereoisomer with the largest groups on the opposite sides of the double bond is the major product, because that's what's going to be the most stable one. Because you can see in here, so there can be some steric due to the 2 methyl groups on the same side, whereas a trans, they are on the opposite side, so making it more stable. Okay, so this dehydration is stereoselective. Dehydration under mild conditions. Now you have a secondary alcohol, POCl3 and pyridine at 0 degrees Celsius. You can form an alkene. No heat is required and the carbocation rearrangements do not occur under these conditions. And here's the mechanism. Alcohol group comes, attack the phosphorus, leave chlorine, and then we have pyridine in the medium. So this is the product that we're going to get. Oxygen has a hydrogen already attached to it. Now oxygen is positively charged. Pyridine comes and remove a hydrogen and forms this intermediate. And then we have not only one pyridine, we have more pyridine in the reaction mixture. It can act as a base, come and take the hydrogen and form the double bond and makes it a leaving group. This is a good leaving group and you form the alkene. E1 dehydration has been changed to an E2 dehydration in this case. Another way to do an E2 dehydration is converting it to a sulfonate ester. Alcohol group, you use tosyl chlorate to convert it to a sulfonate ester. OH will become OTS, sulfonate ester. And then if you used a nucleophile, a strong nucleophile like methoxide, an elimination reaction can take place. Now, when the elimination takes place, methoxide will grab a proton from this carbon and leaves a tosylate or a sulfonate ester. For example, the hydrogen over here. So methoxide can come, grab this hydrogen, form a double bond right there, and then leave OTS, tosylate group. So forms the alkene. Sulfonate esters have good leaving groups for E2 reactions. They cannot be used for primary alcohols because of competing substitution. Okay, so we have talked about the substitution and elimination of alcohols. Now let's talk about oxidation of secondary alcohols. So what happens if you do an oxidation? So we can use these reagents to do oxidation on alcohols. So here's a secondary alcohol, here's another secondary alcohol. You can use chromic acid, H2CrO4 chromic acid, or you can use sodium chromate in the presence of sulfuric acid. Alcohol, when it is being oxidized, it forms a ketone, a carbonyl group, secondary alcohol. OH will become carbonyl group, a ketone. So these are ketones. If you do an oxidation on primary alcohols with chromic acid, what's going to happen? It first going to form an aldehyde, and then it would further oxidizes to completely form a carboxylic acid. And if you want to stop at the aldehyde, you have to use this reagent, PCC, pyridinium chlorochromate, in the presence of dichloromethane. Primary alcohol, if you want to convert to aldehyde, you will have to use this reagent, PCC and methylene chloride. PCC stands for pyridine chlorochromate. Okay, if you use chromic acid, it will go all the way to carboxylic acids. Tertiary alcohols normally cannot be oxidized further, because if you want to make a double bond to oxygen, you have to break one of these methyl groups. This carbon is not bonded to a hydrogen, so the alcohol cannot be oxidized to a carbonyl compound. Oxidation by hypochlorous acid, HOCl. So if you have a secondary alcohol, a hypochlorous acid in the presence of acetic acid can give you a ketone, another reagent that you can oxidize a secondary alcohol. If you use hypochlorous acid on primary alcohol, it can stop at aldehyde. So we found two reagents that can convert a primary alcohol to aldehyde. One is hypochlorous acid, and then the other one is PCC in the presence of dichloromethane. And this is the mechanism of hypochlorous acid. Alcohol get protonated, take the hydrogen from the hypochlorous acid, become a water molecule, protonated alcohol, a good leaving group as a water molecule. So this hypochlorite act as a nucleophile. It attacks the carbon and then it leaves the water molecule. Okay, now this group OCl is attached to this carbon, and then the base can come and grab a hydrogen here and then give its electrons to form a double bond with the carbonyl group, forming a ketone. Another way that we can use to oxidize alcohol are called Swern oxidation. Now for the Swern oxidation, we use dimethyl sulfoxide. This is dimethyl sulfoxide, and this is called oxalyl chloride, CO2Cl2. In the presence of triethylamine, a primary alcohol will stop at the aldehyde. Okay, and a secondary alcohol in the presence of the Swern oxidation conditions become a ketone. Okay, now we're going to move on to ethers. So I'll talk about the ethers in the second part. So we'll stop this section here.